Welcome to day 21 of Advent of Code. I'll be programming in Liquid Haskell, which adds refinement types to the base language. So I'm a little late getting started because I was still working on some of yesterday's problems. So one of the things I wanted to do yesterday was express the assumption we were making about the problem, that you never divided by the variable you're trying to solve for in the type of the expression tree that I was building. And so this is close to working. What I did is we defined a couple of measures that don't have an interpretation. We're treating them as sort of abstract functions, abstract symbols. And then in the definition of the tree, we can explain what they mean. Like a constant doesn't have any humans, doesn't have any variables, and its depth is 0. When we use one of the other constructors to build a tree up, then the depth of that tree is, it's really the height, I guess, not the depth, is greater than or equal to both sides, and the number of humans is the sum. So this doesn't actually calculate it, it's just an assertion about what this constructor forces to be true. And the problem I'm running into is that it seems to have forgotten that the measure is a natural number at inconvenient points. So the error I'm getting here, here's a bigger version, says, well, I know that the number of variables is 0. Number of humans in the original is 0 because you told me that's the case. But what I need is that the number of variables is less than or equal to the value passed in. I don't introduce new variables when simplifying. And this should be trivially true. 0 is less than or equal to any other natural number. But it can't prove that. So I was asking for help on the Liquid Haskell Slack about that, and it ran over. Because, the other thing I was running into is that the case analysis was not working. And that's more or less a Liquid Haskell bug or limitation, that the way that the pairs get handled in a case statement doesn't translate to Liquid Haskell very well. So we can sort of fix that by refactoring to unpack one side of the pair at a time. And this was a suggestion from the Liquid Haskell Slack. And it didn't quite work, but you can see that all these cases check correctly. So I think that the whole thing will work, but this number of humans was tripping me up. Here's the same problem. It says, well, you gave me something with number of humans 0 and depth 0. How do I know that the number of humans is less than or equal to the one that you passed in? So anyway, on to day 22. I'll get that set up and we'll take a look at today's puzzle. All right, we're all cleaned up here. Okay. Move instruction will take you off of the map. You wrap around. Interesting. All right. So let's pull out our. So we're going to use a matrix or a map again. I think we want our matrix code. So let me find that from a previous day. Gosh, when was it? Vector of say 8. All right, let's start from that. So we're gonna pull in data.vector. Going to pull in some read methods. I don't know whether we need these vector methods. So you can write specifications for functions that are already in the library. You just have to use assume. All right. So, but instead of storing trees, we're building a maze of tiles. Right, that has a size, and we're going to use so a tile is empty, or a wall, or a floor. All right. So let's see. So we're gonna read tile. So it's gonna go from a character to a tile. So dot is a floor. Pound octothorpe is a wall. And so anything else is empty. Okay. So there's how we read the first row. Once we read that, we know the size of all subsequent rows. At least we better. I may have to do some editing of the input file, or we may have to pad them out. We'll take a look. Okay. Okay, so read the first row. If the length of the first row is empty, then nothing. Otherwise, read the row and return tiles. The constructor is tiles. All right. So let's copy over the example. Yeah, we're gonna have to pad this out. I don't mind cheating like that. So you know what we're gonna do? We're just gonna take 2 passes over the input. Since we have to write the code to pad anything. All right. Okay. So we can, what's unhappy about here? There it is. All right, so we're going to read the row, calculate its length, and then so the extra is repeat replicate x size minus the row len copies of empty. And return vec from list that and extra. All right. Vector tile. Other direction. No, that's Okay. It doesn't. We haven't guaranteed it's positive. So I guess. Okay. So if rho n is less than or equal to x size, then otherwise, this would be a case where we could continue to return the error like it did before I removed that, but we'll just we'll take the first n elements. Go. Oh, not from S, from row. All right. So now it can verify that yes, we returned a vector of the correct length in any case. So let's width equals maximum over map length SS. I'm still calling this height. I don't need to be maybe. Yeah, that's simplified a lot. Great. We should have done that on day 8. All right, so that reads it in. Now we've got a grid where everything's either empty for the spaces that aren't filled in or a wall or a floor. So we now need to parse the list of directions. I think we may want to use parsec for this. All right, so let's put that in a separate file. That is to keep Liquid Haskell happy. Okay, when was the last time we used this? Okay, so parse the number, I need that. Okay, so we need type directions, which is I'm using turn left, turn right, move. So we're gonna create parsers that just suck up that single character and return. Better get left and right straight. It's going to be very confusing. Okay. There's probably some fancy parser combinator for that. I don't know what it is though. Maybe like this. Yeah, that's the sequence operator I don't actually care about. Yeah, that does not work. About So what we did here, assuming this works. All right, good. So we took our constructor and the function that turns strings into integers, and we compose them, and then we lift those into the parser monad, which has things like errors. And here what we did is return converts turn left into the parser monad for direction. Takes a direction and turns it into a parser direction, basically. And we just sequence that after character right. So these basically mean the same thing. All right, so parse direction. I need to combine them all. Parse vector. So it's parse left or parse right or parse. Okay, and then we need some boilerplate to actually unwrap the parser monad. So if it's an error, it's a left, and otherwise it's a list of directions. Okay, so we want at least one. Great. How's that look? Directions. Great. All right, so that's the other half of our parser. Put that away, go back to our main file and import that. All right, and now we need let's look at our input. Oh, interesting. Okay. Let's be sure to get everything. It would be possible to parse these together. I'm just not, because there's no reason. We can just include this as a literal. later. All right, so all right, kind of cheap, but that's fine. So to carry out these instructions, we need to know our position and orientation. So another data type. So it would be nice to qualify this position in terms of the limits we establish, so we know it's in bounds. We could sure. So let's and then we can create a type is that's position in bounds. So given maze M, then an inbounds position has x pos less than or equal to x size of M and y position less than y size. So we can use that to decorate our other functions and check that we're always ending up in a position that is inbounds. All right, are we still compiling? Wow, I love how it spits out the whole definition for the warning. So let's do left turns and right turns. West. From north we go to east, from east we go to south, from south we go to west, and from west we go to north. I'm wondering whether you should cache the borders, but I don't think that's going to make a big difference. You notice there's no ambiguity about jumping over an empty space in the input, which is good. All right, so let's move one step. So given a maze and a position, return a new position. So our specification is that this is just any maze, and this has to be a positions in bounds. Position in bounds. I'm just gonna call this in bounds. I get real tired of typing all that. And it should return another coordinate in bound and the facing should not change. Great. So I think we're going to want a utility function which is so given our position, I don't know what to call this yet, return what would be the next all right, we're going to do this in two steps. We're going to do what it could be if we did move and none of the topological or obstacles mattered. None of the topology or obstacles mattered. And we'll back that up to one where we're actually paying attention to what's going on. All right, so x, y, so north is y minus 1, south is x plus, is y plus 1, east is x plus 1, west is x minus 1. All right. We could even inline that into the specification language if we need to be to. These are all fairly simple. All right, so we need to look for a wall, and we need to look for going off the edge. So we could go, let's just double check. Okay. Most open tiles, top row tiles, okay. Take you off the map. So this doesn't show going, that sort of does. All right, B and A are connected. So this calculates if we go off the edge, where do we end up? We have to do this before looking if there's a wall in the way. Okay. All right, so we call offset first, we'll pass it to this. Okay, so if so I'm wondering whether we need to encode the idea that at most one of the coordinates can be out of bounds. Otherwise, don't really like using position, but I hate going back and breaking it up into a coordinate type more. So the guarantee this is going to make is that given a pair of integers, it's going to transform into a inbounds position. And this is where knowing that they weren't both bad would help a lot, because if we were able to move diagonally, then both could wrap around simultaneously, but that's not true. So we have to handle it to satisfy this specification, though. All right, so the diagonal case is actually kind of tricky, I think. I'm not sure it's well defined. I hope we don't have to find out in part 2. So that's true. No, it's opposite. And so we have to handle so now we know it's in bounds, so we can do the vector lookup. Okay, so if it's space, shoot, then we need to know which direction we're going. Because if we got there by moving east, then we know how to wrap around to the leftmost. If we got there by going west, then we know how to wrap around. And this, again, we could reduce the cases by 2. If we could convince it that there are only 2 possibilities. Sure. So let's define a type that encodes that. So so this is a pair. I have to I'm not sure this will parse. So if OX equals X, then X, then y does not equal y, else y equals y. So I think this actually is going to have to be our dependent pair syntax instead. I don't think that works. So position, its orientation. All right, we didn't finish this. Let's just comment that out for a second. I want to make sure the liquid Haskell's happy with what we did. These aren't pairs at all. That was kind of silly. Yeah, all right. So this is actually a dependent pair. It should look like that. Oh, okay. So X. Down symbol X position, but it's right there. X. Okay, these were wrong. X pause P. Okay. Let's try qualifying him. Why is this giving us so much trouble? All right, so X. Okay. I think it was just some variable escape there. All right. So now with wraparound, we can say this type is actually a one difference of so it's at most one of them is different. So can we actually use that? Let's just take the specification and re-roll. Okay. Okay, so let nx.ny equals offset x positive alt position y positive facing okay. So if now we got two cases, and only two cases. So x must have moved. So okay, so if we stepped on a space, then we still didn't guarantee that it must have been an east or west move, which is really what I wanted, so that we can only check 2 cases here. All right, let's try this. Okay, so if x equals 0, and rightmost, okay, so there's one case where we moved off the left. Okay, else if x is greater than x size m, then okay. Now let's check y. So if y is the bottommost, and if y is off the bottom, then we want the topmost. No, no. Oh, there's the problem. There we go. All right. Else, okay, so we'll use the same functions again. So if we're going west, then we'll do rightmost. I really should unpack this, because this is gross. All right. Okay. Old y, old x, old facing. I'm pretty sure I didn't get these right. Off the left, find the rightmost. Off the right, find the leftmost. On the same row, go up and find the bottommost in the same column. If we go bottom, find the topmost in the same column. Okay. So I'm really unsure it's going to be able to prove everything we need, but we gave it a pretty strong condition here. Okay, so if it's space, I think this is where we're more likely to have problems. So if new y, new x. And they're all in bounds now. Okay, so that's what we needed. So west is the same as less than 0. East is the same as this. North is the same as this. So I'm wondering whether we could just fold these two cases together. Like, if we violate the first condition, then it must have been because we're going in that direction. All right, let's see what Liquid Haskell thinks. Oh, it thinks I haven't defined any of the functions yet. Maze and a integer and returns a integer. Okay, so before we write them, let's write our specifications. So this almost takes a maze and a x coordinate that is in bounds, so x is less than x size of the maze, and it returns a y coordinate that's in bounds. Okay. So topmost is the same signature. We can't easily specify that is a space, that it is furthermore, it's not empty. We can't do the vector lookup in a specification. So that's not something it can check. There are ways to do it, but they're all kind of gross. The best way would be to do a proof that that is the case. Okay, so this takes a y and returns an x. Okay. Not space empty. Okay, so we now need to take not just the whole maze, but the tiles of the maze. We're just going to write a function to do that. And we're going to take x then y, because we can. Is x, y equals m bang y first, bang x. Okay, so let's just change that to. Right. And the nice thing about liquid Haskell is it knows which bound is which. So if we switch them around, then I did it again. Okay. Tile maze. Copy and paste problem there. All right, getting closer. I'm very worried about this function. Yeah, so now it's spitting out. All right, so what's it saying? It says it's got a position and its x position is A, which is inbound. Its y position is C, about which it knows nothing. So I was, okay, so my chain of reasoning is if nx, so it used to be inbounds and now it's not inbounds, therefore it is the one that changed. And so old y equals y, and that is inbounds. So let's I wonder if we made a mistake by separating these two. I wonder if it's going to be easier to combine them. Because then we've just got 4 cases. And so let's try that. We'll save this and try rewriting it. So if y equals y minus 1, so if and y is less than 0, or of nx, x, and y, then okay, that's pretty slick. Does Liquid Haskell agree? Let me. Oh, right. Else p x and y. Oh, not regional x, regional x, regional x. All right, so it's given us crap about not handling all the cases. One of these days, I will get all the variables right. it's so Liquid Haskell is a Haskell plugin into the compiler, and so all its output is just normal compiler output, and so tools like Emacs work with that, but sometimes they don't work great because, all right, so it looks like the specification type did not survive the unpacking. So what if we call this P? Because I really want to keep the. All right, let's do it this way. Case facing P. So if it's north, okay. So what I'm hoping is that the specification attaches to all those. Except I didn't define them. All right, let's do that. I wonder if that's why I needed. It's not used. I used it below. I wonder if that's why I needed just qualify these. All right, it's looking a little less nice. All right, it knows it's one less. What it's not saying is that it's still greater than 0. It did say. It did say they were natural numbers. Okay, it'd be very strange if it didn't respect the or is Haskell's or not shortcutted? All right, good. The only thing it's complaining about is that we didn't handle all the other cases. So is Haskell's or not shortcutted? I think it's just a liquid Haskell problem then. Well, I really hate that we had to and it's not a big deal, but all right. South is +1. So if new y is greater than equal to y size the maze, topmost south, okay, and then let's do west, so that new x equals x plus p minus 1. If new x is less than 0, then p of rightmost x. All right, and east. +1. All right, how does that look? Looks like it passes the specification. Yeah, all we're getting is warning. Great. So if we made a copy and paste error like this, then Liquid Haskell says, hey, what gives? You promised the facing would remain the same. So, all right, that was a little uglier than I hoped, but it passes the specification. All right, so we need to fill in all these. So these are all vector operations. So let's look at the Look at data.vector. So fold, no. How odd, enumeration, all right. No. We want to search. Indexed would do if we index would do if we had to. I don't want to filter, I want to find the index. Search, there we go. Find index. That returns the first one. Where'd that go? We want to find the last one. Could do find indices, I guess. Can we reverse? We can, although it is O of n times, so it doesn't actually help us unless it's lazy. All right. I don't know what I did to get all this. So I think we need to, I'm almost sure this isn't. Okay, we're gonna write a specification for it. So if it returns an int then and had better be n less than vector length of a. Oh, I didn't give the vector name. A is the type. Okay. So it helps us with topmost. No, it doesn't. It only helps us with leftmost. Okay. T equals t is not empty. Of maze of the tiles in the maze, bang y. So maze y. Okay. So if it's nothing, we didn't find one, this shouldn't happen, so let's just return the 0 index. Okay. Huh. It doesn't believe that 0. Okay, let's all right. Now 0 should always be valid because we said it's a positive integer for this size. This is the same problem I ran into before of the natural valued measure that the type seems to get lost sometimes. Right, this should have type maze to positive number. Let's try that theory out here. No, that's not going to help. Yuck. Let's preserve the non-working version and try again. Maybe it's bang? No. Some type information got lost somewhere. Okay, well, in that context, it doesn't seem to know that the vector we looked up has this size. Let's try that. So give it a maze, and we're going to return a vector of tiles such that the vector length of v equals the x size of m. All right, so oh, okay, we need to say it's a natural number. Does that help? Still doesn't believe that. That's very weird. All right, it accepts that. So it's okay. Does it accept that? Then I don't know why. This doesn't feel right. All right. So let's pick. And reverse, we'll do find indices. So let's give that. type. So if let non-empty. Okay, so effect size then oops, not an arrow. If there's no non-empty, then we're in trouble. So we might as well just pick something. And else return non-empty bang okay, what is it? Length? Length. Okay, does that work? No, it's oh. Okay, good. So let's do topmost and bottommost. So let's do a get column, which will be somewhat less trivial. No, so we want to do a map. Map a function over a vector and return the results. Yes. Okay, so we're going to vector map from the row to row bang x on tiles of M. X. All right, I don't see a complaint. So now we can define bottommost and topmost in the same way. This takes m and an x, trans s for the column. Okay, and topmost, it's like rightmost. No, I switched them around. This is topmost. This is the minimum y index. Given an m and an x, I'm going to grab the column, filter for non-empty, otherwise take the last non-empty item. All right, I think we've got the things we need to finally move one step, which is all right. So let next position equals wrap maze old position. So the new position is the wraparound. But we gotta check for walls. So if get tile, yes. If get tile m if it's a wall, then stick with our old position. Else new position. Great. So, wow, I'm slow today. Nearly 2 hours already. Around. Okay, so maze old position steps. So we can just apply this keep going to the monad page. Don't need that, I don't need that. There's one for vectors. Why does this keep popping open? Wow, I so hate that. Iterated n times, by which we mean iterated n minus 1 times. Gosh, thanks. I forgot iterate was the infinite list. I think I used that, but I actually had to define a defined an infinite list class. All right, so we'll just stick with vector. Even with its horrible convention. Okay, so it takes the integer first, and then a function, and then the initial value. So our function is move one step in the maze, and okay. It's kind of tempting to actually let's return the list. Let's return the list of positions in case we need to. All right, so we're going to take but now I need to think about up by one again. So this will return x and then fx. So you need to take n plus 1, and I'm going to take the tail. So to do that safely, we have to tell it that n is not 0. Is iterate in the standard library? Oh, that's right. I ran into this before. So did I fix it? Yes, so that's what I did, is I overwrote the assumption. I said, hey, iterates at least a million. A list of a million long. All right, so we have to say this should be a inbounds and this should be all right. Great. Okay, so given a maze and a starting position and a set of directions, return a set of positions. Direction. Okay. Okay, so if it's empty, we return the empty list. If it is left, then we don't need to add the turn itself onto the list. Maybe we'll get that. So we do follow directions M. So new position is turn left of facing start. Oh, what did I call it? It's been so long I forgot. Turn left. Okay. Turn right. Nice. Otherwise, it's going to be move N. So we're going to move N steps in our maze from our current position N. So that's the whole list of moves. And we're going to append that onto So we need the last. Okay. So we need to check. We need to separate out these cases. If we ever get a move 0, then just don't move. Otherwise, it's non-zero. So we need the last element in the list. Okay, let's verify that this is of no, because num steps could be bigger. So, oh sorry, length L. I'd like to say N. But our million above is interfering with that. Right? The solver is smart enough to know that million is not actually the biggest N could possibly be. So I wrote an infinite list library. It's just the specifications. So, all right. So it's complaining about follow directions M. All right. We can say that this list has length at least 1 because N is at least 1. All right. Oh, no. No, that was good. All right. Follow direction starting with the last position we ended up in. There we are. Huh. It can't tell that it's greater than 0. Oh, because we didn't include that in our specification of it. We have to go backwards at some point. We'll worry about it later. So we've got everything we need to define this to. Position M maze bounds M. So start position is the leftmost position, non-empty position. Let me check my input a second to see if we need to do a special case. No, there's not a wall there. If there was a wall there, then I'd cry. Zero facing right, facing east. There's this problem again. If it doesn't believe that zero is always in bounds. All right, if I size m is greater than 0, which should be a gimme. That's what we said. It was true of all mazes. Did I define positive right? Wrong? No. N greater than 0. I really don't know what liquid Haskell is doing here, but it doesn't seem right. Okay, so let's read our input. Okay, read our maze. It should have complained way up here that this could be 0. I didn't check it. All right. Okay, so we got our maze. Gonna have to swap that out by hand. So parse, okay, case parse directions of sample dirs is nothing of parse. Okay, so if it's a left, all right, we have our dirs. So then we just need to follow them. Maze are start position of maze And our, oops. Okay, so that's our entire path. It's lazily generated. So we could just look up the last one, but I'm gonna print it out for testing purposes. And we probably need a show method for position. I still don't know the magic. Still don't know the magic incantation over after 20 some days. Instance. All right, let's fire it up. I expect that it's been saving up some errors for us. Like maybe, yeah, now it finally chooses to complain about the width. I don't know why. I think it's because we weren't calling the function before. And so it did have a path. All right. All right, let's run it. Well, that doesn't look right at all. Okay. Oh, that's the input, but still looks bad. Oh, all right. Well, so since it didn't match, it might be okay. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh, it doesn't include the original start position. We explicitly took that off. All right, we can cope. So, yeah, move over to 10, get stuck there. Start moving south. Move from 0 to 1, 2, 3, 4, 5. And move east. Wrap around to 0. Very good. 2, 5, 3, 5. Okay. South. Get stuck against that wall. Good. 4, 7. Okay. 7, 7. Is that 7, 7? Okay, wrap around to 0, 1. Wrap around to 4. Good. 7, 5. Get stuck there. All right. That looks like it. So let's calculate the final password. And we have to add 1 to our coordinates. Once again, I'm going to copy and paste rather than writing another function. I would not normally recommend that. All right, so 100 times the row. So that's the row. Plus 4 times the column, x plus 1, plus north is 3. North is 3, west is 2, south is 1, and east right is 0. All right, so Can we tell this that this is not empty? What is it called? Or isn't there one? Null. Does it not know null? I just checked it, and you got the function. Returns true if and only if the length is 0. I didn't really want to take the length. Really? All right, this I gotta check this out. I'm sorry for getting distracted. All right, try it online. Yeah, you can try Liquid Haskell online. All right, safe last. It goes from int to int. If null, else. Safe last. Okay. Time to ask about that, I guess. And A good deed done for the day, I guess. Six, 0, 3, 2. All right, let's try our puzzle. So I'm going to sub in realtors and the real input. Oops. Hurrah! All right. All right, so we need new wrapping rules for part 2. All right, yes, that can be wrapped into cube. How are we going to represent that relationship? So we can match up rows or columns that are blank or off the edge with their coordinates, with a folding. So we're just, I think, just going to give the folding as an extra input. So this row this set of coordinates maps to this. I may have to get some paper out. It'd be interesting to derive it, but I don't think I have time for that. In fact, we could just put the coordinates into our map. So this will work best if we have an extra thing on every side of the border. So okay, so the row is going to be Can we do this all while reading it in? No, we don't know where it's going to. So we're gonna have to go fill it in. is we have a replicate in vector. I guess we could use identity, but yes, we got one. Do we have to tell it that what vec replicate does? I hope not. Okay. Okay. So our maze. So we're gonna update our maze with a set of jumps. So how are we gonna represent this? Excuse me. Probably makes sense to just draw the lines. It's a lot easier for the little one than for the big one, but it's fundamentally the same issue. It's just figuring out what the coordinates are. And this is Emacs, so I've got line numbers. Well, they're all 50 by 50. All right. Is this going to work? It's not. Because this square needs a jump in both directions. All right, so we're going to have to do it with some sort of other lookup. I kind of like pasting them together, but could we map the coordinates? Into which face they're on? That would be a little easier, I think. Then, all right, so let's Yeah, let's actually undo all that. Yeah, that wasn't a good idea. All right, so we're going to introduce so our face is going to be, hold on a second. We could use Rubik's Cube conventions if I remembered what they were. So we're gonna use this one. Okay, we're going to give them color names. Okay, so we're going to have a function to map the position to which face it is on. Okay, so we're going to call okay, this is going to be the top. So this is white. So this is green. Next to it is orange. Wrapping around is yellow. Blue green is blue. And so this must be red. Green. All right, and it's going to return a face, and what's our coordinate system going to be? So we're figuring out the transitions. I'm just going to use the same coordinate system on all of them. Yeah. Blue. Do we flip it over or do we use the coordinate system as it stands, as it's currently oriented? So should we adopt? I think we should adopt three-dimensional coordinates. Yeah. I think that'll be easier to do the wraparound if if we're at Z0, which is this top row, and we are at x0, y0. So this is the origin of our coordinate system right there. Reversed for you in the camera, sorry. And then we go around the corner, then our z increases by 1, our x stays the same, and our y so yeah, our x stays the same, our y stays the same, and only our z changes as we go down like that. And then when we get here, z changes more time, but then we can't move any further in the z direction, and so we have to decrease y. Yeah, so I'm using a top-down. Right. CL has the same x-axis y, it doesn't, y is -1. C goes from 0 to n. All right. So if y is greater than 0 and y less than or equal to 3, less than 4. Okay, so those are our 3 layers in the unfolded version. So how are we going to tell liquid Haskell what we're doing? Okay, y coordinates. Y coordinates stay the same. X coordinates -8. Okay, so far so good. All right, x greater than or equal to 0. So we're on the yellow face. Can we do this unfolding? I need a bigger piece of paper. I need a bigger piece of paper. Just a sec. All right. Let's draw this out. So we got okay, got white like that. Should grab some scissors too, I guess. Okay, green. Orange. Yellow. Orange. Green. And blue. Yeah, I didn't get it right. All right, so there's this reversed. No. All right, so there's our white coordinates. And then is there another way to describe how this fold works? Off the edge. So we're for N green. I still like my idea of projecting to a 3D coordinate system, but I'm wondering whether it's just going to cause me a lot of hassle because all the directions it's a true fact. all the coordinates. So what are we going to have to do? We're going to have to, when we wander onto the edge of this grid or to space, we're going to have to determine our new location. And it could just write the function to do that directly. Rather than trying to translate to a coordinate and write it, write the translation to coordinates and back, and I can just plot it out. All right. But it matters not which square we're at, but what direction we came from. Because if we're in the corner of the fold, then if we go down, we end one place. If we go down, we end one place. But if we go over, then we end up in another place. So let's get rid of that. And let's just write so given our x and y coordinates and our orientation, return a new position. That's just position to position. Okay, so we use my handy real-world model. So if we're at 0, then we are falling off the top of the white face onto the yellow face, and do so at the top of the yellow. So do we switch orientation? So if we were heading up, we're now heading down. We were on the left-hand side, we're now on the right-hand side. If we used to be on the right-hand side, we're now on the left-hand side. All right, so if we were at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, no, 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so if we're at 8, then if we were at 11, we're now at 0. If we were at 8, we're now at 3. That's the way those two snap together. And we're entering through the top face, so our y coordinate is now all right. That is one edge. So if our y coordinate is, if our x coordinate is 7, and it can be in one of two cases. Okay. I keep hoping that I'll have some revelation about how algorithmically easy this is. I'm going to have to call it quits. I don't think I'm going to be able to get the other star tonight. We'll come back with some better paper prototypes and have the transitions all written out on paper before I code them, I think. Or look at other people's solutions and figure out how they did it. All right, well, we got 1 star. This is our second drop star, maybe. And we found some liquid Haskell strangeness to boot. That's still still think this thing we encountered is just bad. Okay. Have a good evening. Thanks for hanging out. Good night.